Professor Mr. K. Balraj is working as a polymer consultant and teaching fellow in the area of polymer science and engineering at CEG Anna University, Chennai. He has completed AMIE in Electrical Engineering at the Institution of Engineers India, Calcutta and MTech Polymer Science and Engineering at CEG Anna University. He is also pursuing his doctoral research work in polymer technology. His area of specialization includes polymer rheology, polymer processing, characterization and testing of polymers, polymer blends and composites and insulation technology. He has in-depth experience on plastic properties, testing methods and the relevant standards. He has more than 15 years of teaching experience in polymer science and engineering, including instrumentation in polymer industries, engineering plastics, conducting polymers and rubber technology at CEG Anna University. He has guided more than 30 MTech students in their research projects. He has presented more than 20 research papers in the national and international conferences in the area of polymer science. He has published 10 research papers in the peer-reviewed journals.
Welcome to UGC lecture series in polymer science. In polymer science, we are discussing about polymer rheology. In the first episode, we have discussed about what is meant by rheology, what is viscosity, what is the dependence of viscosity and rheology with respect to polymer processing, and some aspects of converting a raw polymeric material into a useful product. That is where the rheology gaining importance. In today's episode, we will discuss about what is meant by non-Newtonian flow, simple shear flow and melt flow in DAX. What is meant by non-Newtonian flow? Why non-Newtonian flow is important for polymeric systems? Because most of the polymer systems do not follow Newtonian law. What is Newtonian law? Newtonian law is that the relationship between velocity gradient and the shear stress is linear. For non-Newtonian fluids, there is no linear relationship between velocity gradient and shear stress. Non-Newtonian flow can be classified into non-time dependence flow, time dependence flow and viscoelastic flow. How a viscous material will behave, a normal viscous material will behave. When you plot strain versus time for a viscous material, there will be a linear increase like this, which is characterized by the viscosity. This is the applied stress and this is viscosity and this is the strain rate. This is for a normal viscous material. What are all the features of a normal viscous material? At low strain rate, it is exactly a linear curve what we have seen in the previous curve. It is a simple Newtonian relationship and it totally depends with time, and stress has a direct function of strain rate and also stress independent of strain. What is a non-time dependence flow? In non-time dependence flow, the shear rate for non-time dependence flow can be represented mathematically by the shear stress as gamma, which is the shear rate, which is a function of shear stress. In rheological studies, there are 4 types of flow that do not depend on time. One, Bingham body flow, pseudoplastic flow, Newtonian flow and then dilatant flow. A typical shear rate versus velocity gradient for non-time dependence flow is as shown. In the y-axis you have the applied stress and in the x-axis the velocity gradient. There is a linear relationship which is shown as Newtonian, and then this pseudoplastic and dilatant. In Bingham plastic flow, it has a threshold stress as represented as tau naught. Up to tau naught, there will not be any flow. Once the applied stress is greater than tau naught, then the Bingham plastic flow starts flowing. First we will see Bingham body flow. Bingham body flow is an elastic solid in which the structure will collapse when the stress applied is greater than the yield stress or the threshold stress. Therefore, shear stress for Bingham body can be represented mathematically as shear stress equal to sum of the viscosity into the shear rate plus the residual stress or the threshold stress. Materials that represent Bingham body flow includes emulsion, suspension with high concentration. Typical examples are paint, printing ink, clay, slurry solution, and of course the plastic emulsions. Next, we will move on to pseudoplastic flow. In pseudoplastic flow, the main property is shear thinning, which means with the increase in shear rate, the viscosity starts decreasing. So, that is what is called as shear thinning, which is an advantage when we convert a raw material into a useful product, either in extrusion molding machine or in injection molding machine. Therefore, during real processing that involves a high range of shear rate, absolutely there will not be any problems for the plastic melt to flow. What happens at suppressed conditions is molecules has higher entanglement, and then it can have random conformation or orientation also. Once with the increase in the shear rate, these entanglements will go away and this orientation takes the direction of flow, and therefore it enhances further flowing. So, this is what happens in pseudoplastic flow. Under the application of a shear force, uncoiling of the molecular chain will occur and the orientation of the molecule increases. Even though the Brownian movement is the movement which is present in the material before the applied shear force, once the application of the shear force will overcome this Brownian movement and hence facilitates better flow. At very high shear rates, the pseudoplastic flow is almost like a Newtonian flow. And with respect to viscosity, pseudoplastic are also called as shear thinning fluids have a low apparent viscosity at high shear rates. In the first episode, we have discussed about different types of viscosities: apparent viscosity, constant viscosity, and low viscosity. The apparent viscosity is the viscosity which is measured from the origin to the specified point in the stress strain curve. This is a typical rheogram for a pseudoplastic substance, shear stress versus shear rate, and this is a typical rheogram for pseudoplastic substance which do have some residual stress. This is a typical relationship between Newtonian and pseudoplastic flow, in which at high shear rates you could find a pseudoplastic curve has a similar shape with respect to Newtonian. To start with, the viscosity curve, the viscosity is high for a, to start with, the viscosity is very high for a pseudoplastic flow, it is almost here. Once with the increase in shear rate, the viscosity gradually comes down and it's similar to a Newtonian flow. Next, dilated material. Dilated material is just opposite to pseudoplastic flow, in which viscosity will actually increase with increase in rate of shear, which is called as shear thickening, which is an unwanted effect with respect to polymer processing. But this dilatant effect can be readily seen with a mixture of cornstarch and water, which is a typical example for some biopolymers do exhibit this dilatant behavior. A typical dilatant curve is shown, in which your the shear stress versus shear rate, the viscosity starts increasing, the curve goes up and up. Dilatant behavior is normally seen in polymers with high suspension such as PVC is a typical example for dilatant flow. Therefore, normally when we want to process PVC, a plasticizer is added which will try to reduce this dilatant effect. These are the materials that are difficult to be compressed under high shear rate. Next, we will move on to time dependence flow. Flow properties that depend with time also depends on the type of shear flow, the flow history, and the molding time it takes. The molding time varies for injection molding to compression molding to extrusion molding. So, these are the factors. Next, the viscoelastic flow. What makes polymeric material interesting in this context is that their time constants for flow are the same order of magnitude as their processing times, irrespective of the process: extrusion molding, injection molding, or blow molding. Or in other words, in very short processing times, the polymer may behave as a solid, while in long processing times the material may behave as a fluid. It goes to both the extreme, from viscous, highly viscous to highly elastic. This dual nature of fluid to solid is referred to as viscoelastic behavior. Next we will move on to time dependent flow. What is meant by time dependent flow? Time dependent flow is with the increase in the shear rate, with the increase in the time, how the viscosity changes, that is going to affect the flow properties. These flow properties that depend with time will also depend on the type of shear flow, whether it is a Newtonian flow or whether it is a non-Newtonian flow. In non-Newtonian flow you have a pseudoplastic or you have dilatancy. In the first episode we have seen about thixotrophy. In all these, the nature of the shear flow do have an effect on the flow properties. And then the flow history. The flow history refers to the profile, the velocity profile, whether it is going to have a parabolic form or it is going to have a very flat flow form. So likewise, and then in the processing, the molding time. The molding time is again very important. The rheological study data, the molding time is taken into account before choosing a particular processing method for converting the raw material, polymeric raw materials into a useful product. First we will see what is meant by viscoelastic flow. What is viscoelastic flow? Visco may viscous and then elastic. So the polymers are good examples for this viscoelastic flow. And polymer, why? Because the time constants are for flow are of the same order of magnitude as their processing times for either extrusion molding or injection molding and blow molding. What is time constant for flow? For example, you have first order systems, second order systems, any polymeric processing operations like your extrusion molding, injection molding can be modeled either as a first order system or a second order system. In first order system you have one time constant, for second order system you have two time constants, and then this time constant and the processing time have a direct relationship or the magnitude are of the same order for a polymeric system. In very short processing times, the polymer may behave as a solid, while in long processing times, the material may behave as a fluid. That is, for short processing time refers to short molding time. The time it takes, molding time is the time the resin takes to fill the mold before it is ejected out as a final product. So therefore, in short processing time, the polymer has to behave as a solid. The long processing time, the material may behave as a fluid, which means the long processing time here refers to the extrusion machine, where you have three sections like feed section, metering section and then extrusion section. The feed section, the polymeric materials, raw materials in the form of pellets or powders are fed in. In the metering section, these materials are converted into a fluid. So it takes long time for conversion from solid to liquid. That is what is referred to as long processing time. This dual nature is referred to as viscoelastic behavior, which is very typical of polymeric processing. In the viscoelastic flow, the dominant flow is of course the viscous behavior. Once the applied stress is removed, it slowly deforms. Therefore, there is a elastic recovery after the removal of the applied stress. This viscoelastic flow has properties in between solid and the liquid behavior. Typical viscoelastic behavior. The polymer is called viscoelastic because it exhibits both elastic as well as viscous. Is also called as plastic, elastic and plastic behavior. Plastic behavior refers to a high viscous flow and elastic behavior refers to a fluid like flow. A typical strain versus time curve for a polymeric system is as shown. At a specified time, for example time T suffix A, there is an instantaneous increase in strain which is elastic. Once then the strain increases gradually, plastic, then it goes down. So therefore, this Instantaneous elastic strain followed by viscous time dependent strain is what we call it as viscoelastic behavior, which is very typical of polymeric systems. Next we will move on to simple shear flow. In simple shear flow, consider a fluid in between two plates of area A. The direction of the flow of the fluid is also as shown. Now a tangential force F is applied to the top plate, which will result in a velocity. This will cause a displacement of the fluid, and then this U is the distance between the separation of the plates, which is a simple shear flow. Now in the simple shear flow, once this tangential force F is applied, this will result in a velocity V, which will cause the top plate to move. Remember that this bottom plate is stationary. Now this will result in the layer just adjacent to the fluid particles to displace in the pattern as shown, but at the bottom of the plate the displacement is there is zero displacement. As a result, you could see a series of layers, which is what we call it as velocity gradient, or in other words, this will have a velocity V1, this one V2, V3, V4, V5, V6 likewise, and then the velocity here is 0. This one represents maximum velocity and this one represents 0 velocity. Therefore, there is a specific velocity gradient that is being developed. In shear deformation, a force F is applied as shown in the figure in the earlier side. Now the top layer is displaced by, for example, U. Now the relative displacement of the two layers is what we call it as simple shear strain gamma. U is the displacement. U refers to the first arrow mark, which is the maximum change in position from here, and then this H of course is the distance of the separation of the plates. This relationship is what we call it as shear strain. Because it is in the tangential direction, it is called shear force. Because of the shear force, a shear strain. Now what are the factors affecting shear flow? First one is the temperature. Flow occurs as a result of polymer chains sliding over each other. The ease of flow will depend on the mobility of the chains and the entanglement forces holding them together. As we discussed in the first part, any polymeric sample is composed of number of chains, and each chain will have different chain length because of the number of molecules that is being attached to each chain. Once the polymer is prepared, that is, it is converted from monomer to polymer, and then once a flow occurs, it depends on this mobility of the chain, how well one chain can slide over another chain, and then all these chains at normal stage are more entangled, and then this entanglement force that holds them together, these two will go away once you increase the temperature. An increase in temperature will result in the mobility, and hence the viscosity will go down. For simple low molecular weight Newtonian fluids, the viscosity will have a direct relationship. That means once you increase the temperature, the viscosity will go down. Next, pressure. In all these discussions so far, we have assumed that polymer melts are incompressible. That means there is no effect due to pressure, which is a normal or a reasonable approximation for most of the application. But however, there are some evidences with respect to injection molding where high pressure values are possible, even up to 150 megapascal pressure is developed in a typical injection molding process. So this increase in pressure will restrict the mobility of the polymer chains, and hence it will increase viscosity. So this pressure will have effect with respect to viscosity only for specific processing methods like injection molding. For most of the other applications like your extrusion molding, the pressure effect is negligible. Of course, the next factor that affects the shear flow is the molecular structure. Molecular structure is the single most important parameter which will have a direct effect on the polymer rheology. Polymer chains are assumed to be highly coiled in the equilibrium state. that is at the normal state, and there is a high degrees of both inter and intra chain entanglement, that is entanglement with respect to the single chain as well as entanglement with respect to the neighboring chains. These are at high degree or at a high state. The coiling and the entanglement will be at the maximum state when the polymer is in rest. Now when a stress is applied, the chain tends to become aligned and disentangled. Once you apply the stress, it is like more or like a coiled wire. Once you remove the once you try to uncoil the wire, it may straighten up. The similar case with respect to polymeric chains. Once a stress is applied, these chains tend to become aligned in the direction of application of force, and it gets disentangled. This will facilitate slippage of the chains, that is one chain will slide over another chain, and an individual molecule is able to drag others along because there is no entanglement. One chain when it is attached to another chain, one chain starts moving, the next chain will also move. As a result, with respect to the external stress, there will be a easy flow with respect to the increase in stress. Now the instruments for rheology measurements. A very popular type of instrument to measure viscosity is capillary rheometer or viscometer. Its function in conditions of load and force is constant or at constant volume rate. In conditions of constant shear stress, measurement of flow rate was taken based on the speed of piston. Pressure at the outer layer of the die is measured using the pressure transducer. This is one way to measure viscosity. The next common method for rheological studies is of course the melt flow index. Any polymer processing industry will have a melt flow index. In fact, when you want to prepare a plastic chair or a plastic cup or any plastic product, then you want to choose either polyethylene or polypropylene. The MFI values are the unitless number, it is only a number. So this will indicate how well this material could be processed, or in other words, what is the type of processing that is suitable based on this melt flow index. Melt flow index is an analysis method that determines the ease of flow of plastic materials. Melt flow rate depends on molecular weight and of course the type of additives that is being added. The melt flow index value allows for direct comparison of materials to each other. So for a R&D engineer, when the number of plastic materials are available, based on this melt flow index value, one can choose which one is good for a given type of application as well as a given type of processing method. And then there are two standard methods that has to be adopted: American Standard Test Methods D1238 and International Standard Organizations 1133. These are the standard test methods accepted worldwide. The melt flow index value has to be evaluated based on these two methods. Of course, the ASTM D138 method we will see in the next slide. Before that, what is meant by melt flow index? The melt flow index refers simply the extrusion of a thermoplastic material through an orifice, very small orifice of specific length and diameter under prescribed conditions of temperature and load. So in the American Standard Test Methods D1238 and International Standards Organization 1133, these are the standard methods to evaluate the melt flow index of plastic materials. These methods are accepted worldwide. The extrusion, next the definition for melt flow index. The extrusion of a thermoplastic material through an orifice of specific length, diameter and prescribed conditions of temperature and load. So this is where the standard methods have been evolved by American Standard and Test Methods, which is followed worldwide. By this method, they will prescribe, for example, polypropylene. What is the temperature? Typical value is 220 degrees Celsius. You have to maintain if you want to find the MF value for polypropylene. Similarly, the load, whether you have to maintain 1 kg load or 2 kg load, and then what should be the length of the orifice through which the polymer is extruded, and what is the diameter of the orifice through which the polymer will pass through. Or in other words, it is also called as melt index, melt flow index, or melt flow rate. All these refers to MFI. All these are collectively called as MFI. It simply means how many grams are extruded per 10 minutes pushed out of a die of prescribed dimensions according to an ASTM standard under the action of a specified load. This is a typical melt flow apparatus where you have this orifice and a heating chamber and the hopper. This is a typical melt flow instrument, and then display device which will directly display how many grams of material is extruded for 10 minutes. So, this is a block diagram. So, this weight is as per the ASTM standard, either 1 kg or 2 kg of weight is applied, and then what should be the piston movement from this point to this point, and then this is the cylinder through which the polymeric resin will flow, and then this is the orifice. Now, they will collect the polymeric resin that is extruded through this for 10 minutes, and then they will weigh. So, for example, 10 grams for 10 minutes means then the MFI value for that material is 10. Low MFI value usually is good for processing. High MFI value, then sufficient care has to be taken for with respect to processing equipments. Summary: in today's class we have discussed about non-Newtonian flow, simple shear flow, and then melt flow index. So, non-Newtonian flow is the basis for polymer rheology, and then with respect to polymer rheology, why polymer rheology is important? Because all the polymeric pellets, either the polymeric resins, either the pellets or in the powder form, this has to be melted and then passed to a mold, and then it has to be converted to a useful product. So, that is where this non-Newtonian flow and then the simple shear flow and is important. And then these polymeric resins are frequently sold in the market on the basis of its density and melt flow index value. However, this melt flow index is just one point on an viscosity curve, which is the apparent viscosity. Plastic extrusion also involves shear rates usually up to 1000 second inverse, and the viscosity measurements are called for to determine the shear thinning behavior. The shear thinning behavior is the behavior which is a typical case with respect to polymeric system, because all the polymeric systems do exhibit pseudoplastic behavior. In pseudoplastic behavior, with increase in the shear rate, the viscosity goes down, which is shear thinning. So, these are the questions viewers has to think of. What is meant by a non-Newtonian fluid? Why when a non-Newtonian fluid goes hard, when you give a force, when a sudden force is exerted on it, and then the difference between shear thinning and shear thickening, and what is the melt flow index? Thank you.